Hello and welcome to the differential protection session. This session consists of 4 parts. In the first part, I will discuss the general principles of differential protection, show how we can make the protection work selective. And then we have 3 parts where I show the different applications for line protection, for transformer protection, and for busbar protection. So let's start with the general topics. What is the principle of differential protection? Differential protection has a pretty easy principle. We draw a circle around our protected device, and then we measure all currents flowing into the device. And normally, according to Kirchhoff's law, the sum of all currents flowing into a device should be 0. We can calculate this sum by summing up individual sampled measured values or instantaneous current values. That is one possibility shown in the lower line of the yellow box. Or we can compute the phases, that means the amplitude and the phase angle represented as a complex value, and sum up the complex values. And these sum of currents, of all currents flowing into a device, is called the differential current, either in phasors or calculated with instantaneous values. We can do that phase by phase. That means we have to multiply this, what you see now, by 3. Do the same thing for the other phases as well. And for a healthy device, we learned this differential current is 0. What is now going to happen if we have a fault? A short circuit. That means from one phase we have a current flow either to ground or into the other phase. Of course, in such a situation, Kirchhoff's law is also valid, but the fault current flowing to ground or into the other phase is not measured. We have no current transformer at the fault location, and that disturbs the equation. And that means in case of a fault, we suddenly have a differential current. That means the differential current is a good indication for a fault. But you see here, I wrote theoretically, of course, if you program such a thing, you cannot ask, is the differential current exactly 0? It will never be exactly 0. That means you must always allow a certain deviation from 0, and we call that threshold. That means the principle is we calculate the differential current and we compare this current with the threshold, and if the differential current is above the threshold, then we say, okay, there must be a fault in the protected zone. And if the differential current is smaller than the threshold, then we say, okay, the device is healthy. So the problem is the threshold. What is the correct value for the threshold? And the issue there is we cannot take a fixed value. If we make the threshold too small, then the protection becomes very sensitive, but we may have wrong trips. If we make this threshold value too high, that means we trip only if we have a significant differential current, then we may not have sufficient sensitivity to catch all faults we want to catch. And I would like to illustrate that a little bit more using 2 examples. So here I have again this equation. We trip if the differential current is above the threshold. You see in the yellow box the equation just for a 2-ended line. There we have to sum up 2 currents, either as phasors or as instantaneous values. And the first case I'd like to discuss is a fault, maybe a resistive fault, on a line, on the protected line. In this case, we expect that our protection relay should trip. So what happens? We measure the currents at 2 ends of the line. Short circuit currents comes from both sides. That means both current transformers measure a certain current flowing into the line fault current 1 on the left side, fault current 2 on the right side. And from that we calculate the differential current. We assume they are in phase, so we can just simply sum up the two currents. That means the differential current in this case is equal to the fault current. And now that means, for instance, if we have a resistive fault, the fault current can be pretty low. And let's assume in this case we have a fault current maybe of 300 or 400 amps. That means our threshold must be lower than the lowest fault current we want to catch. That means if we want to catch a fault of 400 amps, our threshold must be lower than this value of 400 amps. That is one case. Now the other case, and this other case is normally the more critical thing in differential protection, we have an external fault, that means a fault outside the protected zone on the next zone, and there our protection relay should not trip. And what is the situation there? We have a short circuit current through our protected line. That means on the left side, the current transformer sees a fault current, this through current. On the right side, it sees the same current flowing out of the line, so it sees minus IF. From that, we can calculate the differential current, IF minus IF, which is 0. No trip, that is fine. But in real life, of course, it will not exactly be 0. In real life, we will, for instance, have measuring errors in our current transformers. And that means the measurement on both sides will not be exactly the fault current. It will be, as indicated here, the fault current plus or minus a certain measuring error. I call it here delta I. As long as the measurement error is the same on both sides, it will have no impact. The differential current will still be 0. But we can, of course, also have the case that the left side current transformer has a negative measurement error and that the right side current transformer has a positive measurement error. And then the differential current is no longer 0. If we, for instance, assume a 5% measurement error, and one has minus 5%, the other has plus 5%, the result will be that we have a differential current which is equal to 10% of the fault current. And now imagine if we have, for instance, a fault current of 10 kiloamps flowing through the cable, and 10% of 10 kiloamps would be 1000 amps. That means we would, in this case, see a differential current of 1000 amps. That means our threshold value we use for the differential principle must be higher than 1000 amps. That means on the left case we said it must be lower than 300 amps, and on the right side we say it must be higher than 1000 amps, and the result of that is this threshold value must be adapted to the fault case. That means in differential protection we calculate the differential current and compare it with a value which has to be adapted to the fault case. And there are different possibilities to do that. The first thing I would like to show is the traditional concept you find in many differential protection applications. That is the use of the so-called restraint current. And that means we calculate a restraint current just by summing up all currents, by summing up the absolute value of all currents. That means without taking the sign and the phase angle into account. And this restraint current is an indication of how much current is flowing there, and that is used to adapt the threshold value. And what you normally find there is a diagram like this. That means you have on the horizontal axis this restraint current, which is an indication for the amount of current on the line. And on the vertical axis you have the differential current. And then you define in this plane a tripping area. It can look like this orange area here. You see in particular applications it may look a little bit different, but the idea is always the same. And that means as long as you have low currents flowing, that means the restraint current is low, then the limit where the tripping area begins, this threshold value, is lower. And if you have high currents flowing, think about our through fault, then the limit where we do the tripping is higher. So that is just given by this characteristic. If we have a fault in the protected zone, then the differential current is equal to the restraint current. Then we are on this red dashed line. That is the fault in the protected zone. And what you can see also from this diagram is if you have a fault in the protected zone with a very low current, you are still in a white area, it will not trip. That means with this principle, you have a certain level of fault current which must be there so that the protection will react on that. So for very, very low currents, it will not see the fault. That is called the traditional differential protection concept. We use it in our relays for transformer protection, for busbar protection, for generator protection. For line protection, we are going a different approach, because in line protection we often have to deal with different fault mechanisms, with resistive faults, and there we introduced already with C-Protect 4 relays a different approach. This approach is an adaptive concept. It goes again back to the original idea. The question is, what can be the maximum differential current in a certain operating state for a healthy line? That means in this concept, the protection relays permanently measures all the currents and then estimates in this operating states we actually have. It can be a load state, it can be an internal fault, it can be an external fault. In this state, what can be the maximum differential current we can have? Add a little bit of security to that, and if we then calculate a differential current which is higher than this value, then we say it must be a short circuit in the protected zone, then we trip. And with this concept, and we will discuss a bit more in detail what are the different sources for differential current on a healthy line. With this concept, we come to a very sensitive and reliable protection of lines. So, as I said, that's an alternative to the traditional concept. In general, if we compare differential protection with the other protection principles we discussed, like overcurrent protection or distance protection, it has some advantages, but you will see it also has some disadvantages. What is the advantage? It's a very simple principle. No complicated algorithms for impedance measurement. We just measure the currents. We have a clear definition of the protected zone. That is really a nice feature. Remember this story, this discussion for distance protection about how long is the reach of the zone, it's influenced by measurement errors and so on. You can forget all this for differential protection. It protects the line or the transformer from one current transformer to the other one. And you can also make settings which allow you a very sensitive protection. That means we can catch resistive faults. But it also has some disadvantages. Remember, in overcurrent protection and distance protection, the protection relay first of all looks at its own line, but it also looks a little bit into the next line. And if there is a protection failure on the next line, our protection relay sees also this short circuit on the next line, sees that the relay on the next line does not react on it, and can then serve as a backup. That's not possible with differential protection. Differential protection just looks at its own line or transformer, and it's not interested in anything else. That means you must think about additional functions to do the backup. Then if we apply differential protection to lines, then we need a data exchange between the two ends of the line. And this data exchange, imagine if you have a long line, 100 kilometers, you need a reliable data exchange between the two locations. And that can be a thing which is not in all cases very easy. And there is also a certain risk that we react sensitively on saturation. Saturation is an issue where we have to live with. Overcurrent protection and distance protection tend to do underreaction. That means to have a delayed tripping in case of current transformer saturation. In differential protection, we have a certain risk of a wrong tripping in case of saturation, and we must provide additional measures in the protection relays to avoid these problems. So that was a short introduction into differential protection, and in the next chapter I would like to talk about line differential protection.